It's been a real pleasure attending this conference. I think it's been an amazing testament to Evgeny's achievements, especially over the last 10 years, building up a department in his research group in Lincoln. I first met Evgeny in Novosibirsk in the winter of 1980-81. I remember it was bloody cold. And I was dragging my 8-year-old son along with me because my wife had died a few months earlier and there was nobody else to look after him. So that made life interesting. Actually, he came with me to Novosibirsk and Moscow and Leningrad. Nobody complained. Maybe they were just too polite to complain. Actually, everybody was entirely charming and it worked very well. While I was in Novosibirsk, I gave a 2-hour seminar to the algebra seminar with Efim Zelmanov doing a simultaneous translation. But towards the end of my talk, he gave up translating. I don't know whether he was just tired or he reckoned everybody gone to sleep and stopped listening. Anyway, the talk was on the restricted Burnside problem. And especially, I talked quite a bit about Lie relators in Burnside groups of prime power exponent. It's not an active area at the moment, I don't think. We have a pretty good idea of, a pretty good understanding of the multilinear Lie relators in Burnside groups of prime power exponent. The most famous one, of course, is in exponent P, you've got the Engel P-1 relation, which is actually equivalent to a multilinear relation. So, as I say, a pretty good understanding of the multilinear relations. Absolutely no understanding of relations which are not consequences of the multilinear relations. But I think that's just too difficult. We know that they can exist, but where they might arise, who knows? Evgeny, in fact, has made some quite significant contributions in the area of Lie relations in Burnside groups. And especially with connections with the Hughes problem. After my seminar, he told me he had a computer program running as we spoke, working on Lie relators in 2 generator groups of exponent 7. I don't know exactly when it finished. I think it was after I'd left because I think it was running for some time, this program. But he got 2 really significant results out of it. He managed to construct a 2 generator 7 group, which was a counterexample to the Hughes conjecture. And I think even more significant, he managed to produce a counterexample to a theorem of Kostrikin, which I think is anybody could be proud to do that. So it's not quite over 40 years ago, and I'm not still working on the same sort of stuff quite. But of course, I am talking about Engel groups and Engel Lie algebras, and actually Lie relators, but in Lie relators in Engel groups rather than in groups in Burnside groups. So, what is an Engel group? Well, an N-Engel group, if it satisfies the identity x, y, y, y with n y's equals 1. So the n is fixed. I think we had some earlier talks where the n would depend on x and y, but this is fixed. And we know that n-Engel groups are locally nilpotent for n less than or equal to 4. The n equals 2 was Levi, n equals 3 was Heineken, and n equals 4 was Havas and Vaughan a few years ago. But what happens when, what about 5 Engel groups? Well, who knows? I think it's actually comparable in difficulty to the Burnside problem in exponent 5. Actually, John Wilson said to me a few years ago, he pointed out that in the Burnside group of Burnside problem for exponent 5, 5 is prime, but in 5 Engel groups, it isn't. I don't know whether that was supposed to make it more difficult or less difficult, but anyway, as I say, I think, who knows, but I think it's a really difficult problem. what's his name? Charlie Sims. Charlie Sims spent years trying to prove that the two-generated Burnside group of exponent 5 is finite, and he had his computers doing Knuth-Bendix operations, must have spent years of CPU time on it. Of course, he would never be able to prove that it was infinite that way, but he was hoping to prove that it's finite. And actually, I think that if it was finite, the Burnside group, two-generated Burnside group of exponent 5, I think there's a pretty good chance that Charlie would have managed to prove it. So my inclination is to believe that it isn't finite, but there's none of the sort of Olshansky and Adyan methods begin to approach exponent 5. So who knows? Maybe somebody will come up with a brilliant new idea, but it may be just one of those problems that remains unsolved forever. Maybe that's a bit negative. If you take the largest nilpotent two-generator 5-angle group, it's sort of comparable with the largest finite two-generator group of exponent 5. It's actually got smaller class 9. And the nilpotent quotient algorithm gives a presentation on 52 generators, whereas R25 has order 5 to the 34 and class 12. So they're in the same sort of neck of the woods, but of course the largest nilpotent 5-angle group is nilpotent, and angle relations are much harder to understand than power relations, exponent relations. So I think for the time being that problem will remain unsolved. Who knows, though, what happens in the future. But if we look at locally nilpotent groups, so bringing in 5-angle, of course, the other n equals 2, 3, 4, we know they're locally nilpotent. Then there are integers p and c such that locally nilpotent n-angle p groups are globally nilpotent of class at most c for all primes p greater than this capital P. So, for example, for n equals 2, they're nilpotent of class at most 3 for all primes. For n equals 3, as long as the prime is bigger than 5, then they're nilpotent of class 4. That's down to Heineken, I guess. For n equals 4, as long as the prime is bigger than 5, then they're nilpotent of class at most 7. That's Gunnar Traustason. And for n equals 5, fairly recent results of mine that as long as the prime is bigger than 7, then nilpotent of class at most 10. To me, slightly more interesting is that in many cases you can bound the nilpotency class of the normal closure of an element. You can't in 5-angle 3 groups. The normal closure of an element does not have to be nilpotent. I'd really like to know the answer for 5-angle 2 groups. Does the normal closure of an element have to be nilpotent, or can it have unbounded nilpotency class? So I suppose I'm saying this. We're in locally nilpotent, so well, it's not even clear the normal closure of an element would even be nilpotent. But in other cases, for n less than or equal to 5, we can bound the nilpotency class of the normal closure of an element, with the bound depending on P. So even when they're not globally nilpotent, that means you can get a bound on the class of a finitely generated one. For n equals 2, the normal closure of every element has been, and that's actually just another way of stating the two-angle relation. For n equals 3, the normal closure of an element is nilpotent of class at most 2. And that, I guess, is down to Heineken, though you can prove it very easily using the nilpotent quotient algorithm. For n equals 4, Gunnar Traustason produced these bounds. He's a whiz at hand calculation, and for reasons I'll explain in a minute, you have to do some hand calculation for these p equals 2 and p equals 3. I did check his claim for p equals 3 on well, using the nilpotent quotient algorithm. Starting a few weeks ago, it actually ran for about 3 weeks on my computer before it finally completed. So these are non-trivial results, certainly for a computer, maybe not for Gunnar. He's a clever chap. And then for n equals 5, as I say, for p equals 2, we don't know. For p equals 3, they don't have to be nilpotent. And then for p equals 5, you get nilpotency class 6 as the normal closure, and so on. It's interesting the way it can be high for smaller primes and then drop off for bigger primes. The method of proving these results for 4 and 5 is oh yeah, well, that's Bruce said that. The method of proving these results for n equals 4 and n equals 5 come down to a theorem of Graham-Higman from 1956. He came up with a beautiful proof of the restricted Burnside problem for exponent 5. He did exponent 5 before Kostrikin solved it for general prime P. And the first theorem then is if L is a 4-angle Lie algebra of characteristic 5, and you've got generators X and then an infinite number of generators A1, A2, A3, where all the A's commute, then L is nilpotent. His was a very clever hand calculation. He estimated the class would be somewhere below 50. Actually, with computers, you can show that the class of this Lie algebra L is 12, and that the normal closure of the X has nilpotent class 6. And then there's this, he came up with this very brilliant argument that if in L, the ideal generated by X is nilpotent to class C, then if you have any angle 4 the algebra of characteristic 5, M, then every element in that M, in that Lie algebra M, the ideal generated by it is nilpotent to class most C, even though the other generators don't commute. And the argument is really very neat, and I'll try and explain it. Otherwise, if you're interested, you have to go back and read Higman's paper. But the idea is that suppose you have a lead product in M with C plus 1 Y's and a whole lot of other entries. And you want to prove that it's 0, right? So suppose it's got C plus 1 Y's and say K different entries, which we might as well call A1, A2, A3 up to AK, even though we're not assuming that the A's commute. Then it has to lie in the ideal by the first theorem, it has to lie in the ideal generated by commutators AI, AJ. That means that you can rewrite it as a linear combination of commutators with C plus 1 X's, and only instead of K other entries, only K minus 1 other entries, where one of the other entries is an AI, AJ. But then you just treat that AI, AJ as a single element, and you've rewritten your commutator with C plus 1 X's and K other elements, C plus 1 Y's, sorry, and K other elements as a commutator with C plus 1 Y's and K minus 1 other entries. And you keep on repeating, and of course, eventually it has to be 0. And then you get the corollary that if this class in L of the ideal generated by X is C, then finite degenerated groups of exponent 5 are nilpotent of class at most CD. So that solves the restricted Burnside problem in exponent 5. That's because the associated Lie rings of groups of exponent 5 have characteristic 5 and satisfy the 4-angle identity. If we go back a bit to the previous slide, as I say, Higman's method was used to get these results for 4 and 5 as well as Engel relations, you get other multilinear Lie relators in Engel groups. Essentially, if you've got to say, let's take n equals 4, so you've got this relation x, comma y, comma y, comma y, comma y, and you replace x by x1, x2 up to xk, and replace y by y1, y2, dot, 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 up to yl, where l is greater than or equal to 4. And if you expand all that commutator and pick it out and pick out in the full expansion the terms which are multilinear in x1 up to xk and y1 up to yl, then that gives you a Lie relator, a multilinear Lie relator of weight k plus l. If you take k equals 1 and l equals 4, you just get the multilinearized Engel 4 relation. So using Higman's idea, you can get these results. But it was especially tricky for n equals 4 for these p equals 2 and p equals 3, because because this Lie algebra L, Higman's algebra, isn't nilpotent in this case, but even though the ideal generated by X is nilpotent, so you couldn't just shove it on a computer and do it. You have to think about it a bit. Of course, the results for n equals 5 are machine computations by a student of mine a few years ago called Dagmara Million. I'm always a bit suspicious about hand calculations, because actually the literature is full of detailed hand calculations which have bugs in them, are wrong. And people are still referring to classifications of groups of order p to the 6th, which are full of bugs. And even though the bugs are known and have been fixed, nobody bothers about the fixes and just uses the original dodgy classification. So I'm always a bit suspicious about hand calculations, but Gunnar is very reliable, and in fact I did recheck using computer as much as I could most of his claims, and checked through the proofs as well, even the thinking type of proof. Now what about, so that's enough on Engel groups. What about Engel Lie algebras? Well, we know from Zelmanoff's solution of the restricted Burnside problem that n-angle Lie algebras are locally nilpotent. So whereas in groups we don't know that n-angle groups are locally nilpotent, we do in Lie algebras. And there's another really beautiful theorem of Zelmanoff who proved that n-angle Lie algebras of characteristic 0 are globally nilpotent. So that there's just, no matter how many generators, they're all nilpotent of a given of the same class, at most that class. And if it works in characteristic 0, then it has to work in characteristic p as long as p is big enough. It's not very hard to see that, but might even be true because of the compactness of first order calculus, or whatever you call it. Not first order, well, whatever. So for every n, there have to be integers capital P and C, such that n-angle Lie algebras of prime characteristic little p, which is bigger than this fixed big P, and nilpotent of class C. So again, going back to n equals 2, now Lie algebras are not groups. They're all nilpotent of class at most 3. In fact, as long as the characteristic isn't 3, they're nilpotent of class 2. For n equals 3, as long as the prime is bigger than 5, then the class is no bigger than 4. Well, I'm lost for a moment. No, anyway, I was about to say something. I don't dare risk saying it. For n equals 4, as long as the prime is bigger than 5, then the class is most 7. Then what I really want to talk about today is a fairly recent proof of mine that for n equals 5, as long as the prime is bigger than 7, then angle 5 Lie algebras of characteristic P bigger than 7 are nilpotent class at most 11. To do that, we need to bring in, well, both Lie superalgebras and some representation theory of the symmetric group, which is way outside my comfort zone, but there we go. I've learned how to use it. So what's a Lie superalgebra? It's a Z2 graded algebra L, sum of L0 direct sum L1 with a bilinear bracket product, so that L0, L0's contained in L0 and L1, L1 is contained in L0, but L0, L1 and L1, L0 are contained in L1. Then just a bit of notation, elements in L0 are said to be even, and elements in L1 are said to be odd. And if A is even, then we set mod A equals 0. And if A is odd, then we set mod A equals 1. And odd and even elements are said to be homogeneous. But the real thing is you've got to have some identical relations which they must satisfy. And so the first one is a bit like is sort of corresponds to the anti-commutativity relation in Lie algebras, that B comma A is minus A comma B in Lie algebras, but you fiddle the sign so that if A and B are both odd, then B comma A equals A comma B. And then the next thing is a sort of twiddle of the Jacobi identity. There's a really beautiful way of building Lie superalgebras out of a Lie algebra, which we're going to be using shortly. So you let G be the associative algebra generated by a whole lot of generators, E1, E2, dot, 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 dot. So it's associative, subject to the relations that EI squared is 0 for all I, and it's sort of anti-commutative. EIEJ is minus EJ EI for all IJ with I not equal to J. And then you get a basis B for this associative algebra consisting of all possible products EI, EJ, dot, 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 EK with 1 less than I, less than J, less than, or so on, less than K. And you can write G as Z2 graded algebra, where G0 is spanned by the products of even length and G1 is spanned by the products of odd length. And if G is in G0 and H is in G, then GH equals HG. But if G and H are both in G1 in the odd part, then GH is minus HG. Oh, that's straightforward enough. So what's that got to do with Lie superalgebras? Well, if you let K be a Lie algebra, and then you form K tends to G, call that L, and you define a bracket product on L by setting A tensor G, comma B tensor H equal A, comma B tensor GH. And you extend to L by linear. I mean, it's easy to check. You get a Lie superalgebra. Set L0 equals K tensor G0 and L1 equals K tensor G1. And then that's a Lie superalgebra. So next, we need to look at the representation theory of the symmetric group. If you take the symmetric group on n letters and the group algebra of it over the rationals, then the identity element is a sum of primitive idempotents which correspond to some mysterious objects called Young tableau. For each partition, M1, M2 up to MS of this capital N, where you take them in descending order, M1's greater than or equal to M2, dot, 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 MS. We associate a Young diagram, which is an array of n boxes arranged in S rows with mi boxes in the ith row. So if n equals 5, there are 7 possible Young diagrams. You can have one row with 5 boxes, or one row with 4, and one row with 1, and so on. And so these correspond to partition 5, 4, 1, 3, 2, and so on. So, and you then get a young tableau from a young diagram by filling in the n boxes with 1 up to n in some order. I mean, maybe this is all trivial stuff to most of you, but never mind. We then let H be the subgroup of the symmetric group of order n, which permutes the entries within each row of the tableau, and let V be the subgroup of symmetric group on order n, which permutes the entries within each column of the tableau. And you set E equal to this thing, so sigma sine pi row, where pi runs through all the permutations of the column entries, the entries in the columns, if you like, and rho corresponds to all the permutations of the entries within each row. And then the key thing is that 1 over ke is a primitive idempotent of Q sim n for some k dividing n factorial. And the identity element can be written as a sum of these primitive idempotents. And that works too as well for any field f, as long as the characteristic is co-prime to n factorial. So we make use of that in the proof of this theorem about 5-angle Lie algebras. So we let K be the free 5-angle Lie algebra generated by A1 up to A12 over a field F where F has characteristic 0 or prime characteristic P bigger than 12. We want to prove that all Lie products A1, A2 up to A12 or any permutation of A1, A2 up to A12 come out as naught, because we want to prove that the class is 11. So if you let M be the subspace of this Lie algebra spanned by all commutators A1 sigma, A2 sigma, A12 sigma, where sigma is in the symmetric group of order 12, odds 12 letters, then you get a natural action of F sim 12 on M by letting a permutation just act on the indices. And so we want to prove that A1 up to A12 is naught. And that is just enough to show that this subspace ME equals naught for all primitive idempotents in F sim 12, because A1 up to A12 is acted on by, well, 1 is a sum of these E's. And if ME equals naught for every single one of these E's, then M will be naught. I'm just going to look at one particular example. This is one particular young tableau on 12 cells. And you have to fill in the integers in some order. Actually, it doesn't matter how you do it in the way, as far as I'm concerned, it doesn't matter, but I've done it in this particular way because the idea is to split this tableau up into 4 strips, some of them horizontal and some of them vertical, 4 disjoint strips. And I've done the numbers. So the first strip is a vertical strip, 1, 2, 3, 4, 5. And then you get 3 horizontal strips, 6, 7, 8, 9, 10, and 11, 12. And what we pick out the symmetric groups on these 3 strips. So we let S1 be the symmetric group on 1, 2, 3, 4, 5. S2 be the symmetric group on 6, 7, 8. S3 be the symmetric group on 9, 10, and S4 be the symmetric group on 11, 12. And you pick a left transversal for S1 in V. S1 is a subgroup of the permutation group which permutes the entries within each column. And so you let A be a left transversal for S1. And then S2 cross S3 cross S4 is a subgroup of the permutation H, which permutes the entries within each row. So you pick a right transversal. So it's a left transversal for V and a right transversal for H. And then you let theta be a sum, be the sum over this left transversal for S with a sign, because we need the things in V need a sign attached to them. And we let phi be the sum over this right transversal for S2 comma S3 comma S4 in H. And then you can sort of decompose this E in the top left of this, the slide, as you pull out the theta on the left and the phi on the right, and then you're just left with uh, the sum just over pi in S1 and rho in S2 cross S3 cross S4, again with a sign pi rho. And that the idea is that to show that ME equals naught, it's sufficient to show that M acted on by this lot is naught. The trick then is this is in L, but we form this in K, this free 5-angle Lie algebra, and you tensor it with this thing G, and you get a super algebra, a super Lie algebra, or Lie super algebra L. And the idea is you go down the you split it up into the you define A, B, C, D in L corresponding to these strips that I picked on the go back. We have this strip, the vertical strip 1, 2, 3, 4, 5, and then the 3 horizontal strips. And so you let A be correspond to the 1, 2, 3, 4, 5, but because you A1 tensor E1 plus A2 tensor E2 plus plus A5 tensor E5, and then you B, C, and D correspond to the 3 horizontal strips. The vertical strips correspond to permutations which have a sign attached, so you just want E1, E2, E3. But the horizontal strips, there's no sign attached to the permutations, and so you multiply by 2 E's at a time. And similarly with C and D. And the idea is that to show that this thing is 0, it's enough to show that the subring ABCD inside L is nilpotent of class 11. And I'm not, there's a paper on the archive which explains all this, and I'm not going to go into too much detail here. But the basic idea is, if you think of a Lie product of weight 12 with entries A, B, C, D, and 6 entries A, well, the A is a sum of, 5 entries A. A is a sum of these 5 things. And if you expand it all out, you get these 5 spots where there was A1, you'll get A1, A2, A3, A4, A5, 120 terms with running over all possible permutations of A1, A2, A3, A4, A5 in these 5 places. You can never get an A1 in one place and another A1 in another place, because the E1 squared is naught. And because of the E's sort of anti-commute, you don't just get a sum of 100 over the 120 permutations, you get an alternating sum over the 120 permutations, which is exactly what you want for the sign pi of pi in S1. And similarly, if you think of an entry, if you think of 3 entries B inside the product, again, if you expand everything out, you'll get A6, A7, or A8 in those 3 slots, but in all possible permutations, but there's no sign because the E6, E7 commutes with E8, E9. So what you've done then, instead of having to work in a 12 generator Lie algebra, you have to work to deal with this particular young tableau. You have to work in a 4 generator Lie super algebra, and any tableau, any young tableau on 12 cells, you can always split it up into 3 or 4 horizontal and vertical strips. So you reduce the problem of proving that this 12 generator Lie algebra is nilpotent to proving that a whole bunch of 4 generator Lie superalgebras are nilpotent. And whoops, press the wrong button, sorry. So how do you go about that? Well, for primes, we really have to deal with 11 as well, but I'm going to ignore that. There's ways around that because we wanted for the representation theory to work, you need the prime bigger than 12. So for primes 13, 17, 19, this is just a relatively straightforward calculation. I mean, there's dozens of different cases, over 40 different cases, the young tableau that you have to look at, but each one is a pretty straightforward calculation for any given prime. In principle, you could write a nilpotent quotient algorithm for graded Lie superalgebras over the rationals. The standard way nilpotent quotient algorithms in Lie algebras work, and the P quotient algorithm in groups, is you go up class by class, and in each class you build a basis of left norm Lie products or left norm group commutators, and you enforce the angle relations at each class. The trouble is that this leads to a combinatorial explosion in the denominators of the structure constants of the algebra. They really got completely out of hand. In theory, if you just keep track of all the bad primes that occur in denominators, and also, of course, when you're working over the rationals, you may have a relation which was divisible by a prime p, and it just automatically factored it out. So you'd have to keep track of those sort of primes as well. But in principle, you could do the calculation over the rationals. As long as you kept track of all the bad primes, you go back and handle them separately. But I gave up on that. What you really want is you want to carry out your calculations over the integers. I came up with this way of doing it with 3D superalgebras over the rationals, have a basis consisting of basic Lie products C together with the basis elements C comma C, where C is a basic Lie product, which is odd. And with this basis, the structure constants given the Lie product of two basis elements are all integers. The normal way of nilpotent quotient algorithms, as I say, use just left norm products. I couldn't find a way of doing that so that getting a basis for the Lie superalgebra, where when you had a basis of left norm products, the structure constants were all integers. Actually, they weren't too bad. They seemed to come out with 2s in the denominators, and that's all. And actually, probably I could have handled that. But I thought, well, why not just go with basically products or basically commutators as your basis, and then the structure constants are all integers. For the Russians in the audience, they're probably more used to Chershov basis in free Lie algebras. In the literature, there's 3 standard ways of getting a basis in the free Lie algebras: the Linden basis, the Chershov basis, and basically products using a whole collection process. They really all come to much the same thing. You take an associative word in the generators of your in the free generators of Lie superalgebra, and you wrap it round on itself so the right hand end joins up with the left hand end, and you get a circular word. And all these three bases for 3D algebras, Linden and Shershoff and basic Lie products, they just correspond to different ways of putting the brackets on a circular word. So for example, if you had a circular word ABA, I mean, so you have to wrap it around, then you just get the basic commutator B comma A comma A. If you had AB, you'd actually end up with B comma A squared. So for the Lie algebras, the free Lie algebras, you just take the basic Lie products that come out, where the circular word doesn't give you a square. But for the super algebras, you do want some of the squares when the C is odd. And that's the same. You can take the Linden basis together with C comma C, where C is an odd thing in the Linden basis, or you can take the Shershoff basis together with C comma C, where C is an odd basic element in the Shershoff basis, and so on. Curiously enough, the first guy who wrote a p-quotient algorithm in groups was how are we doing? Oh, I've got to stop soon. Was MacDonald, who is quite a clever chap, but he used the wrong collection process. He used Hall collection, which is I'm plugging here as giving you the basically commutators. And he used he used basic commutators in his thing, and that for those two reasons his program never worked. But never mind. So I wrote a program to compute ABCD up to class 12 using a basis of basic commutator C in elements C comma C, where C is on without enforcing any Engel relations. And so just do the Engel relations at class 12, and you get 27,200 Engel relations, each an integer linear combination of the 13,860 basis elements of grade 12. So it's all quite horrendous, really. I stored the relations in this huge integer matrix. As say, the structure constants are all integers, so we get an integer matrix. And in principle, you could check that the rank of the matrix is 30, full possible rank, 13,860. And then the elementary divisors only involve primes p less than or equal to 7. But it didn't work because Magma just gave up. So what I did was I picked two 13,860 by 13,860 sub-matrices, so the full column rank, which were randomly picked subject to being non-singular when read as matrices over GF11. And then Magma can compute the determinants of these things without too much trouble and check that the greatest common divisor only involved, of the two determinants, only involved primes p less than or equal to 7. In some cases, I did need to get 3 determinants, but just 2 or 3 determinants was enough with all these 40-odd calculations to work out, to show that for primes p bigger than 7, the thing was always 0. There's just got 1 minute left to give one really rather surprising result. Calculators with the nilpotent quotient algorithm show that 4-generator 5-angle Lie algebras, so these are Lie algebras, all 4 generators even, not super algebras, they have class 10 rather than class 11 for all sorts of primes, 11, 13, 17, 19, something. And it seemed very likely that it would be class 10 for all primes bigger than 7. It turned out not to be the case. One particular calculation with 4 even generators gave this 15,791 by 8,400 relation matrix. And I had to use 3 determinants, randomly chose determinants, 8,400 by 8,400 to get anywhere with this. Divided the determinants out by powers of 2, 3, 5, and 7, and computed the greatest common divisor of the result. And this greatest common divisor turned out to be the product of three large primes. I'm not going to read them out. These, I think, what Charles Liam Green calls telephone numbers. And I've never seen anything like that before. I mean, there's no theoretical reason why it shouldn't happen, but it turns out that 4-generator 5-angle Lie algebras do have class 10 for all primes p greater than 7, except for these three large primes. Well, as I say, of course, there's no reason why it shouldn't happen, but it just never does seem to happen, this sort of thing in practice. So there we are, I'll stop there.